Consider the physical architecture of a modern processor operating near its thermal limits. Every calculation has a specific cost in heat and time, and the way Rockstar balances that cost is the central mystery of the Rage 9 engine. Technical analysis of the official trailers establishes a clear baseline for the game's performance: a native resolution of 2560 by 1152, the use of temporal upscaling like FSR or PSSR, and a locked target of 30 frames per second. The engine renders an internal 1440p image and then uses upscaling algorithms to reconstruct the final 4K output seen on the display. Despite these resolution-saving techniques, the performance target remains rigidly set at 30 frames per second. This creates a technical paradox. Temporal upscaling is designed to reduce the load on the graphics processing unit, which usually allows developers to push for higher frame rates. Many assume this frame rate top is a result of limited graphics power, but the rendering data suggests a different bottleneck. Evidence indicates that Rockstar has shifted the primary processing burden away from the graphics pipeline and onto the central processing unit. Standard graphics optimization logic cannot explain Rage 9's performance constraints. To find the answer, we have to look at the engine's internal architecture. Between the release of Grand Theft Auto V and the announcement of the sequel, Rockstar spent 13 years reconstructing their engine architecture to support physically based rendering. This reconstruction relies on two pillars: a lighting model based entirely on ray tracing, and a massive expansion of procedural physics. These systems require the hardware to continuously calculate a live reality, rather than simply loading static pre-rendered environments. Calculating these live interactions generates a constant, heavy demand for CPU compute cycles. Understanding this specific shift in how the engine handles data is the only way to decode the game's true hardware limits. We can see this shift most clearly in the rendering pipeline, starting with the core lighting model. Rockstar has replaced traditional rasterized lighting fallbacks with a ray-traced global illumination loop, or RTGI. This system intersects with every physically based rendering material pass. Every frame, hardware calculates how light vectors bounce between the global illumination system and the world. Integrating lighting so deeply into the materials creates a high, immutable baseline for hardware utilization. Because the engine lacks a traditional lighting backup, developers cannot simply turn down the global illumination to gain more performance. Since the lighting logic is non-negotiable, the available rendering budget is compressed before any other action occurs on screen. To manage this heavy lighting load, developers use specific engineering workarounds to reclaim power for the graphics unit. This grid represents the native 2560 by 1152 array. The engine processes fewer pixels than native 4K, then uses temporal injection algorithms to computationally fill missing data until reaching a 4K matrix. This allows GPU utilization to drop, recovering processing power. Using 1440p as the internal base is a deliberate choice to ensure the graphics unit isn't overwhelmed by the ray-traced lighting. This available headroom indicates that the graphics unit is not the primary hardware constraint preventing higher frame rates. If the GPU has available cycles, then the 30 frame per second floor is being dictated by the CPU. The CPU's primary task is managing the thousands of unscripted physics interactions occurring across the world map. Most games use pre-recorded animations, which are easy for a processor to play back. Rage 9 uses procedural physics, which requires constant mathematical calculation. These reactions are generated in real time, based on the specific impact force involved in an interaction. The CPU must simultaneously calculate the precise location of an injury and the physical state of a character the moment the impact occurs. This diagram shows the mathematical complexity required to resolve a single character's reaction. Each input requires a dedicated set of calculations. In a dense scene, the CPU must duplicate this entire calculation matrix dozens of times for every active character. This results in thousands of concurrent physics calculations executing every second. Because these reactions are unscripted, the CPU cannot predict them. It must resolve the math instantly as events unfold. This processing load increases as the environment becomes more crowded and the geometry more complex. This dense simulation matrix converts the open-world map into a massive, volatile, real-time mathematical equation. The relationship between the CPU and the GPU follows a strict order of operations. The CPU must fully resolve every physics interaction in the simulation before it can send the resulting instructions to the graphics unit to render the frame. Handling the math for massive crowds creates a delay in the pipeline while the graphics card waits for the simulation to finish. This dependency creates a hard limit on how many frames can be dispatched to the screen each second. The graphics card is effectively waiting on the CPU's resolution, meaning further GPU optimizations cannot increase the final frame rate. Every frame rate has a frame time budget, the exact window of time the hardware has to complete its work. Here are the 33.3 milliseconds available to deliver 30 frames per second. The CPU's physics simulation consumes the majority of this time, leaving the remainder for GPU ray tracing and upscaling. But at 60 frames, the simulation math completely overflows the 16.6 millisecond budget. Achieving 60 frames per second on current hardware would require stripping the open world of its unscripted logic and dense character populations. The locked frame rate reflects an architectural choice to prioritize systemic simulation fidelity over pure speed. GTA 6 establishes a framework where the complexity of the procedural reality, rather than the pixel count, defines the absolute boundaries of performance.